So, good morning everyone. Today we are going to cover some practice problems of Heisenberg's uncertainty principle. So, the first question read that a proton is confined to nucleus of radius 5 multiplied by 10 to the power minus 15 meter. So, calculate the minimum uncertainty in its momentum. What is the minimum uncertainty in the kinetic energy of the proton? Okay. So, first step is to know that the maximum uncertainty in the position, that what could be the uncertainty in position, because without knowing uncertainty in position you cannot find uncertainty in momentum. So maximum uncertainty in the case of nucleus is its diameter, that is it will be double of the radius. So double of radius is going to be 10 to the power minus 16 meter. Hence when you apply Heisenberg's uncertainty principle, the corresponding uncertainty in momentum is going to be this. We know that the Heisenberg's uncertainty principle says that uncertainty in momentum multiplied by uncertainty in position is greater than or equal to h bar by 2. So we have applied the same formula. So in this way, when you do the basic mathematics, you get uncertainty in momentum to be 1.054 multiplied by 10 to the power minus 20 kilogram meter per second. Now the main and most important argument in such case is that uncertainties, as I always did tell you, that they are always comparable to the main quantity. So uncertainty in momentum would be comparable in order with the order of the momentum itself. So we could assume momentum to be the same value, because these values are so small that we could do that. So when you calculate the minimum kinetic energy, you will use this formula, that kinetic energy is momentum square divided by 2m. And when you again do the basic mathematics, you put the value of mass of proton, you get the energy, kinetic energy to be 0.206 million electron volt. And for the mathematics part, basic calculation, we are not going to do that, because for that we are allowed to use our calculator, and every basic data will be given that in that question paper itself. Now let us look at the second question. The average time interval that elapses between excitation of an atom and the time it radiates energy is 10 to the power minus 8 seconds. This is the average time. Okay. So like the atom is being excited, so it will radiate energy when it comes back. So this is 10 to the power minus 8 seconds. Now we need to calculate uncertainty energy of the emitted photon and the limit of accuracy with which the frequency of emitted radiation may be determined. So let me tell you very clearly that what happens. Suppose that we have two energy level. First is E1 and second is E2. It is lower and it is higher. So when excitation happens, the electron will move from E1 to E2. But we know that the excited state is not permanent, so it will again come back. And when it will come back, what will happen? It will have to set off the extra energy. So extra energy will be set off by emitting an photon with energy h nu. So nu is the frequency of that photon. So this is what it is happening here. They are emitting photons. Okay. So we know that here we are going to use the energy time variation of Heisenberg's uncertainty principle, that is delta E multiplied by delta T is greater than or equal to h bar by 2. And let delta E and delta T be the respective uncertainty in the energy and time. So when you apply Heisenberg's uncertainty principle, you get delta E to be h bar divided by 2 times delta T. And we know that delta 2 and T would be approximately equal to T when we consider the order. So we are going to use the value 10 to the power minus 8. And when you do the basic calculation, you get delta E to be h upon 4 pi into 2 into 10 to the power minus 8. And this delta E is h multiplied by delta nu. Okay. So in this way we get the change in frequency, which is around 3 into 10, 3.95 multiplied by 10 to the power 6 hertz. Okay. So extra knowledge, what you get that sometime question may ask you to explain your answer or outcome. So what you need to do, we need to say that we have the range of frequency from nu to delta nu plus delta nu. Okay, so this is range is actually this. So hence the emitted radiation must be the band of the waves, not the single wave. Now let us move to the next part. Let find the average time that the atomic system remains in the energy state whose spectral lines width is 10 to the power minus 4 angstrom for lambda is equal to 4000 angstrom. So we have lambda, that is wavelength given, that is 4000 angstrom. Okay, and we have a spectral width also given, that is delta lambda is 10 to the power minus 4 angstrom. This is here we have given a spectral line width. Okay, so hence from this equation we could get energy, that is energy is nothing but hc upon lambda, and when you find the derivative of energy, it is going to be delta E is equal to minus hc delta S square upon delta lambda. I am just differentiating the whole thing with respect to lambda, and for energy we need to have magnitude only, so we applied this magnitude one, and when you put the whole thing, it gets the minus sign gets out, and we have hc divided by lambda square multiplied by delta lambda. Okay, and when you when we substituted the value, like for hc we used 1240 electron volt nanometer. For lambda square we have used 4000 angstrom square, and for a delta lambda we have used 10 to the power minus 4 angstrom. When you do the whole calculation, you get change in energy to be around 77.5 multiplied by 10 to the power minus 9 electron volt. And from this, if you know the energy, uncertainty in energy, you can always know the uncertainty in time by using this formula. So in this way, uncertainty in time after some basic calculation will be 4.25 into 10 to the power minus 9 second. So now let us move to the next question. This question is a high value concept, and it may come someday in our examination. So in a Stern-Garlach experiment, a collimated beam of silver atom is produced by vaporizing silver salt, and the temperature is 1200 degrees centigrade. So if the beam travels 100 centimeter, use the uncertainty principle to find the order of magnitude of the smallest spot that can be recorded on the detector. Okay, beam is traveling 100 centimeter. So what is this spot? The diameter of the spot. So at first what we should do, we should try to find the velocity of the silver atom by applying the kinetic theory. So what we will do, we have temperature. So from temperature we can get that, but let us understand the concept first. And from the velocity we could find time taken to cover 100 centimeter of distance. If you know the velocity, if you know the distance, you can obviously know the time taken to cover that distance. And thus we would have information about the uncertainty in time, because if you know the time taken of the round of the same order, we will have uncertainty too. And then we could find uncertainty energy by using the Heisenberg's uncertainty principle. And from uncertainty in energy we could get uncertainty in momentum, and from momentum we could finally get uncertainty in position, which would be the smallest spot. So this is the whole concept, and this concept is very important. Okay, so that is why we have done it explicitly. Now let us solve it. The velocity of silver atom would be given by 3 kt by m whole under root. This is from the kinetic theory. We have used this formula. Kinetic energy is half 3 by 2 kt in kinetic theory, and for the motion it is half mv square. When you equate that, we get this expression for the velocity, and the mass is obviously for the silver atom. Thus, time taken to traverse 100 centimeter would be 1 meter divided by the velocity. So, time obviously comes m divided by 330 whole under root, and as the uncertainty is in the same order of the time, so uncertainty in time is the same, that is m divided by 3 kt whole under root. Okay. Thus, change in energy is nothing but h bar by upon delta t. Okay, because we can say that for the easy calculation part, delta E multiplied by delta T is approximately equal to delta, h bar. Okay, and here if even if you are not taking h bar by 2, still we are correct, because the main formula is delta E multiplied by delta T should be greater than this. So h bar is obviously greater than the half of h bar. So in this way we could get the minimum energy uncertainty, which is given by this expression. Okay, and energy could be written as, because this energy is going to convert as kinetic energy, and that kinetic energy will actually transform into the momentum. So energy is nothing but change in momentum whole square divided by 2m, and when you do the same thing, you get change in momentum, that is uncertainty in momentum, okay, is given by 2m multiplied by 3 kt by m whole under root, and then overall under root. So this now uncertainty in momentum could be converted into uncertainty in time by using this expression. Again, we have this expression for this, that delta p delta x is approximately equal to h bar. Whenever we need to calculate things only, we need to use this formula, because that is going to be easy. This half 2 is not being used, and still we are correct. So in this way we finally arrive at our uncertainty in position, that is h bar divided by 2m multiplied by the velocity whole under root. Okay, and now each and everything here is a constant, and mass is obviously 108 times the mass of hydrogen. That is the case of the silver atom. So everything you will get in examination hall. We are not required to even remember this, they give it to us, but it is fine. K is Boltzmann constant, T is the temperature in the Kelvin format, and now we got that delta x is 6.99 multiplied by 10 to the power minus 7 meter. So this is the smallest spot that can be detected as the smallest spots, which corresponds to the maximum position uncertainty. Okay, so this is the diameter of that. So you just need to know that what is the most important part, and this concept is the most important part. That how we are arriving from temperature, we are finding velocity. From velocity, we are finding time to cover the distance. From time, we are finding energy uncertainty. From energy uncertainty, we are finding momentum uncertainty, and from momentum uncertainty, we are finding position uncertainty. So this is what the whole thing looks like. So this graph is very important. Okay, graph or flowchart, whatever you call it. Now let us move to the next question. So what the other question says, if a component of angular momentum of the electron in hydrogen atom is known to be 2 h bar, and it is within 5% error, so that its angular position in the plane perpendicular to that compound cannot be specified at all. Okay, let us do it. So according to the uncertainty relation, okay, in the angular momentum and angular position format, we can write this expression, that is delta L multiplied by delta theta is approximately equal to h bar, and delta L is obviously uncertainty in angular momentum, and delta theta is uncertainty in angular position, and it is in radian, let me tell you. Now according to question, delta L is 5% of 2 h bar. It is given here. Okay, if the angular momentum is 2 h bar, then the accuracy is within 5% error. Okay, so in that way, delta L is actually h bar by 10. When you calculate that, the 5% of 2h bar is 5 by 100 multiplied by 2h bar. And from uncertainty principle, delta L is nothing but h bar divided by delta theta, and it is h bar by 10. So theta is 10 radian, like delta theta, which is greater than 2 pi. So now observe that the component of the angular momentum cannot be greater than 2 pi. This is the main idea. See, how could the component of angular momentum could be greater than 2 pi? So angular position in the plane perpendicular cannot be specified, as the question asked us to do so. Now let us move to the next question. An electron of energy 200 electron volt is passed through a circular hole of radius 10 to the power minus 4 centimeter. What is the uncertainty introduced in the angle of emergence? This is very good question. It is being passed from the circular hole, or we could call it a slit. Circular hole, slit, and the radius is very small. That is, it is 10 to the power minus 4 centimeter. That is, it is in the micrometer range. So we are asked to find the uncertainty introduced in angle of emergence. Like this is the slit. Electrons are going like that. That electrons may come out like this. So out of the original direction, what is the angle of emergence? And I can call it a possible question in future. Why? Not exactly this question, but something related to this concept, because same thing has been asked in the past. So let us solve it. We have the energy of electron, that is 200 electron volt. So we could easily find the momentum. Momentum is 2m kinetic energy whole under root. When you put the whole value, we get 7.6 multiplied by 10 to the power minus 24 kilogram meter per second. Also, we have circular hole of radius 10 to the power minus 4 centimeter. So this would be the uncertainty in position. We know our concept that uncertainty is either around radius or diameter, and they are so small that they don't create much difference. Okay, the order would be nearly same. Like if it is going to be either minus 29 or minus 30 or minus 28, so they are not going to create much difference for us who are observing from the macroscopic world. Okay, the ultimate idea is to understand the idea. Okay, an idea is to stick around the order and not the magnitude. So 2r or just r is not going to create much difference. So now the fraction error in determination of momentum would be error in the determination of angular emergence. Okay, we know that we could calculate the fraction error, that is delta p divided by p. Okay, and this is just going to be 6.9 into 10 to the power 6. Okay, this is such a less quantity. So the same error would also transmit to the angular emergence. Okay, so this is going to be delta theta 2. Okay, and this is the schematic here. We know that if suppose that this is the momentum on the schematic diagram, then change in momentum would be in the perpendicular direction, and when you apply the tan theta, it is going to be perpendicular upon base, that is delta p divided by delta just p. Okay, and because delta theta is going to be so small, so delta theta is going to be just delta p by p. And I think here we have a small mistake, that is it should be minus 6. Okay, you see that let me tell you, it is minus 20 and it is minus 24. So obviously in the numerator we are going to get a sign which is going to be minus. So we are done with that. Now let us see the same question which I was just talking about, which is our PYQ. Okay, that a electron with 4 kilo electron volt from a source fall straight on a target which is 50 centimeter away. So find the radius of the electronic spot due to uncertainty principle, assuming focus to be perfect. From energy we can get momentum just like that we did in the previous question. So momentum is nothing but 3.413 multiplied by 10 to the power minus 22 kilogram meter per second. Now calculating the corresponding uncertainty in momentum, because if the target is 50 centimeter away, because 50 centimeter difference would create the uncertainty. So we know that delta p is going to be h bar upon delta x, and theta, which is key concept we just learned here in this diagram. So we are using again that theta is going to be same for both change in p by p and change in x by x. So when we do that, we get theta in the term of momentum to be h bar divided by p times delta x, and theta in the term of position is delta x divided by x, that is delta x divided by 50 centimeter, that is 0.5 meter. When we compare, because they both are theta, so they will both should be equal. So from here we get delta x to be this value. Okay, delta x is nothing but h bar divided by 2 pi whole under root, and we know h bar is 1.054 multiplied by 10 to the power minus 34, and momentum we had just calculated from energy. Okay, we got this energy, we put it here, and we got this value. So when you did that, we get delta x to be 4.094 multiplied by 10 to the power minus 8, obviously in meter, because we have been considering everything in SI unit, and which is uncertainty in the position along the screen. So radius, because it is obviously the diameter of whole spot, the radius would be half of it, that is 2.047 multiplied by 10 to the power minus 8. So we are done with all the important questions which are either PYQ or SPYQ for the Heisenberg's uncertainty principle.